Hello, you are warmly welcome to this lesson on engineering drawing or technical drawing. Today we are going to learn how to draw epicycloid. So first of all, what is an epicycloid? In order to define what an epicycloid is, let's demonstrate this. Let's look at this demonstration. So let's imagine we have this circle, this bigger circle with a center over here, and then we also have this smaller one with the center over here. Okay, now the radius of this circle will be from the center to the circumference of the circle, and the radius of this circle also be from the center to the circumference. Okay, good. Now let's imagine we have a point at this particular part of this smaller circle. This bigger circle is called the directing circle. Okay, directing as in DIRECTING. And then this smaller one is called the rolling circle. So what is going to happen is that this point over here, when this smaller circle is rolling like this, look at what is going to happen. You see that the point moves up, then the point now comes down, and then we stop here. So we say that this smaller circle has undergone one complete revolution. Now an angle theta will always be formed. Okay, so in order to obtain the value of this theta, we divide the diameter of the smaller circle by the diameter of the bigger circle. So the bigger circle is this one, that's this one here, and then this is the smaller circle, or this one is known as the rolling circle, and then this is called the directing circle. Now this point forms something like, let me take it back. So it's something like this. So if it rolls, we are going to have something like this, and then the epicycloid will be this way. Okay, and then it will end here, and then we have this circle here, something like this. So what we do is that we have to divide this circle here that we divide it into 12 equal parts. Okay, something like that. I'm not doing it well, but we divide into 12 equal parts. We'll do that with our instruments right now. So when we divide into 12 equal parts, using the value of theta, we draw the epicycloid. Now, so we define epicycloid as it's generated by a point that is that's rolling on the circle. Okay, so this circle rolls on this bigger one. So a point on this smaller circle here, a point on this circle that rolls on this bigger circle. Okay, so when the point rolls, it forms kind of a curve, and that curve is what we call the epicycloid. Okay, so now let's see how we can do that using our drawing instruments. Let's take a question. But before we take the question, this theta is equal to the diameter of the smaller circle, that's this circle, over the diameter of this bigger circle. They'll multiply that by 360 degrees. That's the value of theta. Okay, now we can take a question. Okay, so this is the question we have. We have a 40 millimeter diameter circle rolls over the circumference of another circle of diameter 120 millimeters. So assuming no slip, trace the path of a point on the circumference of the rolling circle for one complete revolution. Now from the demonstration we just did, we know what one complete revolution means. Now a 40 millimeter diameter circle, so this is the circle that is rolling. Okay, so they are telling us that the diameter of this circle is 40 millimeters. So to obtain the radius of this circle, we just divide the 40 by 2 to obtain the radius of this circle. First of all, let's represent them on our sheet here. So we have to identify our directing circle. So the directing circle, that's the stationary circle, that was the bigger circle in the initial demonstration we're looking at. So this would be the directing circle. Okay, good. So one other thing we have to take note of is that all lines that are not part of the figure we need, we have to represent those lines with thin lines, not with thick lines. So I'll do it this way, something like this. Good, I believe you can see that. Okay, good. Okay, so now let's see the bigger circle's diameter is 120 millimeters. So to obtain the radius, we divide the 120 by 2. So 120 divided by 2, that's 60 millimeters. So let's find 60 millimeters on this line. So 60 millimeters, I'd like to find my 60 millimeters over here. So we have this and that. Okay, so that's our 60 millimeters. Now to obtain this theta, we had this theta, ds over dv times 360. So let's go and find that theta. So the ds, that's the diameter of the smaller circle, is 40 millimeters, right? So we have this 40 millimeters. We divide that by 120 millimeters. Now multiply by 360 degrees. So what answer are we getting for that? Okay, so that is 120 degrees. Please, it's not 120 degrees Celsius, okay? It's 120 degrees. So let's use this to find our 120 degrees. Okay. Okay, I think this it. Yeah, everything is on point. So our 120 degrees is going to be at this side. So let me use my rule to neatly get this done. Okay, so this is the 120 degrees. I'm trying to deepen it so that it will be seen clearly. So what we'll do is that we stand here, then we open to the 60 mark. That's the 60 mark over here. Then we cut this arc, we draw this arc. So we have to indicate that this angle here is 120 degrees. Now the smaller circle's radius is the diameter is 40 millimeters, so the radius will be 20 millimeters. So let's measure the 20 millimeters from here. So we have this. Yes, so 20 millimeters. I stand here, cut, then I stand here. Okay, let me clean this to create space. Okay, I've cleaned that, so let's continue. Okay, so this is our small circle. Now what we have to do is that we have to divide this small circle into 12 equal parts. There are so many ways we can use our set squares. We can use to divide this small circle into 12 equal parts. But I'm intentionally going to use a more difficult way to divide this. What I'm going to do is that since the total angles in this circle is 360 degrees, we divide 360 by 12 because we are dividing the total angle into 12 equal parts. We are going to get 30 degrees. So what I'm going to do is that I'm going to mark 30 degrees with the same radius around the circle. That's what I'm going to do. Just for accuracy's sake, let me look at this. So I also do the same here. Then I also do the same thing here. Then for accuracy's sake, let me check this. It's also on point. Now what I have to do is that I need to get my 90-degree division here. So to get my 90-degree division, what I'll do is that I have to divide this length from here to here into 2. There are so many ways we do this, as I said. So it's not compulsory that I use this method, but I just want to use this one. Okay, so get that. So I do the same thing over here. So I divide this, do the same thing here, do the same here as well, then I do that here. Okay, good. So now I have to join that, but before I join it, I want to make sure that these arcs I've introduced are very small and they are not even seeable. Okay, so let me quickly do that. So I have to make sure that it passes through the center, it's supposed to pass through the center. Yes, I think everything is on point now, so we can just draw this like this. Yeah, so this is what we have. Okay, so let me clean this because people don't usually use this method. I just decided to use this. Okay, now we have to, let's continue dividing this into 12 equal parts. You have to make sure that the radius is still the same value. Okay, good. Now we stand here. You see that when we mark, we get this 30 division here, right? So we have to also stand here. We mark the 30 here. We mark the 30 here. We stand here. We mark here. We mark here. We also stand here. Okay, we already have that. I think that's it. Good. So now we have to join the point. Okay, so we take this point, then we join it to this point. So we take this point too, we join it to this point. We take this one, we join it to this point. Then we take this one, we join it to this point. Good. Now we've neatly done that. Now the next thing we have to go and do is that we have to label what we have. Okay, now it doesn't matter whether you label it in the anti-clockwise direction or in the clockwise direction, but most important is that you start from the bottom for the epicycloid. Okay, but if it is the hypocycloid, you have to rather start from the top. So we start here with 0. You can choose to go like this 1, or you can choose rather write the 1 this way. They go in the anti-clockwise direction, but I want to rather, sorry, they go in the clockwise direction, but I rather want to go in the anti-clockwise. So 1, 2, so we have 3, 4, 5, 6, 7, 8, 9, 10, 11. Okay, that's good. So now what we have to do is that we take this back. We've already done for the 0. So what we do is that we stand at 11. Okay, we make sure that we draw an arc, but we make sure that this arc is passing through both 11 and 1. Okay, so you start at 11, you draw, but you stop here where the angle 120 degrees ends. You do same for 10, then 2. So you draw. As I said at the beginning of the video, you have to make sure that these lines are all constructional lines, or they are thin lines. Now we also have to stand at the center here. Then we do same. So we stand at the center, then we do same. Then we stand at 9. Make sure that it's on 9. It also has to pass through 3. Good. So good. Now we stand at 8. You have to make sure that it also passes through 4, and that is it. We go to 7. Make sure that 7 and 5, the arc passes through both 7 and 5. Then we stand at 6 as well. So 6. Good. Now the next thing we have to do is that we have to divide this into 12 equal parts. We have to divide this line from this one into 12 equal parts. Okay, good. So let's do that as well. Okay, so dividing this into 12 equal parts, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, then 12. Okay, so that is it. We've divided into 12 equal parts. So now you go back, you take your rule, and then you draw lines from the point here, the center of the bigger circle. You draw lines to intersect all the arcs you drew. Once again, these lines should be constructional lines. Okay, So we do same for all the divisions. Do that for this as well, for this as well, for this also do for this one, for this one, for this one, then the last one. Good. So we are done. Now we are almost there. The next thing we have to do is that we have to label. Okay, so we'll look for the center line over here, and from here all the arcs that we drew, this is the center line, this one where the pencil is. So you start labeling from the first one. You call this one C1, you call this one C2, you call this one C3, you call this one C4, that's center 4, you call this C5, C6, C7, this will be C8, this will be C9, this will be C10, this will be C11, this will be center 12. Okay, so now we are almost done. So what we'll do is that with this same radius, that is this radius of 20 millimeters, with this radius 20 millimeters, yes, I think that's it, right? Good. You stand at C1, then you open to line 1. Okay, so this line 1, then where they intersect, you mark an arc there. You stand at C2, you open to line 2, you get another arc there. You stand at C3, open to line 3, another arc there. You stand at C4, you open to line 4, another arc there. You stand at C5, open to line 5, another arc there. Oh, I almost messed that up. Anyway, let's move on. You stand at C6, you open to line 6, another arc there. You stand at C7, open to line 7, another arc at line 7. You stand at C8, open to line 8, another arc there. You stand at C9, open to line 9, another arc at line 9. You stand at C10, open to line 10. So this is line 10, another arc here. You stand at C11, open to line 11. You have this arc at line 11. You stand at C12. So C12 is going to end here. Now the only thing you do is that you take your French curves. So let's get our French curves, and then we draw the curve through that. Okay, good. So this is what we call the French curves. Okay, this is what we call the French curves. So we're easy to join all the points we've drawn, but we have to do that carefully. Okay, so we join the points either we join one point to another, or if all the points fall in line, we can join 3 points together. Okay, but we don't use our hands to do that. Let's take notes. Okay, so in order to do this, let me do this. So I have this point here, I have second point, I have third point, fourth point, that's fine. So I stand here with this. Okay, I think for the, can I join all the 3 together? Yeah, I can join all 3. In fact, all the 4 of them can be joined. Okay, now this line should be very deep because that is what we are looking for. Okay, so very deep. Now let's join the other points. I'm supposed to clean this thing here, but I wouldn't redraw the lines for time's sake. Okay, so let's see how we'll do this one. I'll join this one this way. Okay, make sure that these lines are very deep. Good. Then now you join this line to this one. Okay, so let's join this line to this one. You're going to get something like this. Good. let's move on. So also join this line to this one, and I stand here, join this to that, stand here. Can I join all the three together? Let me see. I think, yeah, we can do that. Okay, we can join all the three together. Then I'll join only this one, and then the last one will go through like this. Good. So you see the shape we have, and this is what we call the epicycloid. Okay, and that's how it is drawn. It's a very simple stuff to do. So you can try this on your own. You get some examples if you have some past questions from your seniors, or you can just bring out figures from your mind, and then you use this to solve some questions. But you are supposed to get something like this. So what it means is that this shape we have, that's from here up to this, is the curve that this point forms, when it moves across or along the bigger circle. Okay, so this point, at the beginning of the video I said the point moves up, and then at the 6th center it begins to move down, and then at this point we call that one revolution. Okay, so that is it. That's the video on epicycloid. I hope it helped you. Thank you very much for your time. All the best. Bye bye.